Similar to the concept of angular speed, there is angular acceleration. For angular acceleration, we usually use the symbol alpha. So the average angular acceleration, similar to the average linear acceleration, it's equal to the change in the angular speed divided by the amount of time necessary to accomplish that change. The instantaneous angular acceleration is equal to the change in the angular speed over time for a very, very, very small time interval. So the units of angular acceleration are radians per second squared, similar to meters per second squared for ordinary acceleration. And the signs for angular acceleration follow the same convention as those for linear acceleration. So if the rotation is speeding up, then alpha, the angular acceleration, is the same sign as the angular velocity. If the rotation is slowing down, then alpha has the opposite sign to the rotational velocity. Next, let's look at the special case of constant angular velocity. So if you have an object that is either going around a circle with a constant speed, or you have a rotating object that is rotating with a constant angular velocity, so the rotation is not speeding up or slowing down, then the angular acceleration is equal to 0. In that case, we can make an analog with linear motion. So we know that if you have a constant velocity situation, that the displacement is equal to velocity times time. And this only works when the acceleration is 0. Similarly, if the angular acceleration is 0, then we can say that the angular displacement is equal to the angular velocity times time. So you basically can write down the same equation only with angular quantities instead of ordinary linear quantities. So let's use that to do this example. What is the angular speed about the rotation axis of the Earth for a person who is standing on the Earth's surface? So for that, we have this person who is standing on the surface of the Earth. So we'll just redraw that here. And the person is standing on the surface of the Earth, and the Earth is rotating about its rotation axis. And so that means this person is going around in a circle. And since they are going around in a circle and the Earth is rotating at a constant rate, then we can figure out what the person's angular speed would be. So we know, since we have constant angular velocity, the rotation of the Earth is not speeding up or slowing down. Then we can write down the expression for constant angular speed or constant angular velocity, which is that the angular displacement is equal to the angular velocity times time. So that means that the angular velocity is equal to the angular displacement, or the angular speed is the angular displacement over time, the amount of time that it takes to accomplish that angular displacement. So let's think about this person going all the way around once as the Earth rotates. So for the Earth to rotate once around completely, that's an equivalent angular distance of 2 pi radians, because if the Earth rotates once, then the person will go through a full 2 pi radians, and that happens in 1 day. 1 day of rotation for the Earth. So we want our angular speed to be in radians per second instead of radians per day, so the rest of this problem becomes one of unit conversion. So we know that 1 day is 24 hours, and then one hour is 3,600 seconds. And so the angular speed of the person as they go around as the Earth turns is going to be 7.27 times 10 to the minus 5th radians per second. So a fairly slow rate of rotation, as one might expect, since the Earth is not rotating super fast. Now, if you have constant angular acceleration, previously we were looking at constant angular velocity, but if the angular acceleration is constant, so you have something that is rotating and the rotation is either speeding up or slowing down at a constant rate, then you can make an analog between the equations for constant ordinary, constant linear acceleration, and write down those same equations with angular quantities instead of linear ones. So v equals v naught plus at becomes omega equals omega naught plus at. And this means the same thing just with rotational quantities. So the final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. And a similar thing can be done for all of the other motion equations. So any of the constant angular acceleration equations work in linear, both in linear land and rotation land. It's just that for rotational equations, you need to use the rotational quantities.